So this P4 video is on qualitative descriptions of work and energy without calculations. There'll be another video to follow that will cover the calculations associated with these things. So first of all, what is energy? Well, it's basically a useful thing that physicists have made up because it's what we call a conserved quantity, and conserved quantities are very useful. What a conserved quantity is one that doesn't change over time. So another example would be the total momentum of a system, for example. So this is kind of summarised in the idea called the conservation of energy, that energy can be transferred from one type to another, but cannot be created or destroyed. Now, P6 tells us this isn't strictly true because we can change energy into matter and matter back into energy, but for the purposes of P4, this is true. Okay. So the most useful energy types you need to make sure you understand for P4 are gravitational potential energy. So that's the energy an object has because of its height in a gravitational field. So if you move an object higher above the surface of the Earth, then it will gain gravitational potential energy. And the two quantities that affect how much gravitational potential energy an object has are the weight of the object, so an object with more weight will have more energy, and the vertical height, so the higher off the ground it is, the more energy it will have. The second one is kinetic energy, so that's the energy an object has because of its motion, because it's moving. And the two things that matter there are the mass of the object and the velocity or the speed. In the equation it says velocity, but actually because you're squaring up the velocity, you can happily use speed when you're calculating kinetic energy and it will make no difference at all. So just bear that in mind. And then the final type that's actually quite useful is thermal energy, and we'll kind of explain why in a minute. You don't really need to understand exactly what factors affect that, or indeed how to calculate it, but it is useful to know that it often occurs in these problems, and we'll see why. Other energy types are chemical, nuclear, elastic potential, electrical potential, sound, and magnetic potential energy as well. Some of these you might encounter. We'll see an example with chemical energy from a fuel later on, but the three that I've listed are the most important ones. Okay, so energy and work. Well, what is work? If you look in the formula sheet, you'll find an equation that says that work done is equal to energy transferred, and that's exactly what work is. Work is done whenever a process of transferring energy from one type to another occurs. And in order to do some work, we need to move a force through a distance. That formula is on the formula sheet as well. We'll look at it again in a second. And it's quite useful to think about the fact that different types of forces are usually involved in different energy transfers. And in particular, we want to link the three types of energy we've talked about to particular types of force. So the first useful force is weight. And weight forces always transfer energy between kinetic energy, KE, and gravitational potential energy, GPE. So when an object moves up, it always gains gravitational potential energy, and that usually causes it to lose kinetic energy. So if we throw a ball up in the air, it starts off moving upwards quickly, and it slows down as it goes upwards. So it's losing kinetic energy and gaining gravitational potential energy. And the reason that's happening is because of the conservation of energy we talked about before. As the object moves upwards, the weight force does some work, transferring its kinetic energy into gravitational potential energy. When an object moves down, the opposite happens. It loses gravitational potential energy and usually gains kinetic energy. We have to say the usually there because other forces that are present can influence that. Okay? So, the other useful force to know about is forces that are grouped together under the term drag. So that includes things like friction and air resistance. And frictional forces are in some ways easier. They always transfer kinetic energy into thermal if the object is moving. Okay? So that's because the drag forces by definition always point in the opposite direction to the motion of the object. So if an object is moving to the right, the drag forces on it will be pointing to the left. If an object is moving down, the drag forces will be pointing up, and that is always true. Okay, very useful to remember that. Okay, so let's have a look at some examples then. We'll start simple and build up the complexity. So we've talked about this one a little bit already. A falling object with no air resistance. We often ignore air resistance in physics because it's useful to do so to simplify situations down. So the only real force acting on this object is the weight. So as we let it go, it accelerates downwards. The weight force is speeding it up. Okay, and this links obviously back to the idea of resultant force that we talked about before. That the weight there is a resultant force. It's going to change the momentum of the object. So you can see the energy and momentum pictures are kind of two different sides of the same coin. So it's moved through a vertical height difference. And so in terms of describing the energy changes, which you might have to do for things like 6-mark questions, as the object falls, the weight force moves through a distance, and the weight force does work transferring the gravitational potential energy of the object into kinetic energy. And it's often useful to draw a diagram. So the way this diagram works is I've got the energy types in green, the transfer is represented in as the red arrow there, and which force is moving to do the work and transfer the energy is written above the arrow. So this is a nice simple one to start with. Okay, so what we can do is we can add air resistance into this. So I've put a drag force on there. I've simplified this a little bit because as the object falls, the drag force on it will increase as it goes faster. I've kept it the same here just to keep it relatively straightforward. Okay, we may get onto a video later on about terminal velocity, in which case it's important to think about the drag force gradually increasing as the speed increases. But we're going to keep it constant. So same thing, we drop the object, it's moved through a vertical height difference again. Now this time though, we've got two forces doing work. The weight force still transferring gravitational potential energy into kinetic, but at the same time, the drag force does work transferring that kinetic energy into thermal energy. Okay, so the overall diagram now looks like this. The gravitational potential energy transfers to kinetic from the weight, but at the same time, the drag force transfers some of that kinetic away into thermal energy. And so if you think about this, it's an obvious overall effect. If we put air resistance in, the object is going to be going slower when it's dropped through the same height because the drag force is trying to slow it down. But often you have to describe this specifically in terms of energy, so you do need to be able to use this language of energy transfer to do that. And if you get a 6-marker and you're asked to describe it, then by all means sketch the diagrams and sketch the energy transfer. It will help you to plan your answer, and you may well get credit for it separately. Okay, some more interesting examples now. We'll go back to our picture of the moon orbiting around the Earth, which we looked at when we looked at the resultant force. So this is an example of a moving force doing no work. And this relies upon a subtlety about the definition of work done that's in the formula sheet, and it's boxed in red here. The work done by a force is the force multiplied by the distance moved in the direction of the force. Now, if you remember, in our moon orbiting example, if we assume the moon's orbit is totally circular, then the yellow arrows representing the gravitational force are always pointing towards the centre of the Earth, and the blue arrows are always pointing along the circle. So they are at right angles to each other. Okay? So that means that there's no movement in the direction of the force at all. It's all at right angles. And that means that that gravitational force does no work. Now that might seem a bit odd, because it's clearly doing something. But if you think about it, all it's doing is changing the direction of motion of the moon. It's not changing its speed. If its speed isn't changing, its kinetic energy can't be changing, right? And we know its kinetic energy doesn't change because you don't have the moon moving faster at some points than others, okay? So that makes total sense, okay? That the gravitational force is changing the direction the moon's moving, but it isn't speeding it up or slowing it down. And also, the moon isn't changing height above the Earth's surface, so it can't be changing gravitational potential energy either. So the weight force can't transfer between the two of them. Right, another example. This might be an answer to the question, why is it harder for a car to accelerate uphill? So let's look at the forces. This is slightly more complicated now. We've got multiple forces. And when you're doing energy transfers, it's best to consider them separately because all the different forces do different energy transfers. You wouldn't want to talk about resultant force here, really, because the resultant force is made up of the real forces involved, and they each have their own separate transfers. Okay, so we've got the normal reaction, remember, which is a force at right angles to the surface. That's going to be important, very important in a second. By definition, that's what the word normal means. The weight is obviously pointing downwards or towards the centre of the Earth, and the motive force is pushing the car in the forward direction. And on the flat here, it's moving horizontally. So only one of these forces is doing work. Only the motive force is doing work. It's the only one that's not at right angles to the motion. So therefore, what's happening is chemical energy, because the motive force is provided basically by the engine, and the engine runs on a fuel, which is a store of chemical energy, is transferred into kinetic energy. So the car accelerates. We've ignored air resistance here again just to keep it simple, but obviously in the real situation there will be air resistance and drag. So just like with the ball falling through the air, some of that kinetic energy will be transferred to thermal. But just to keep it simple and focus on the slope aspect, I've left that part out. Okay, so if we put the car on the slope, then the force diagram looks a little bit different. Useful to be able to draw these as well. The weight still points down. That's often a mistake people make. The weight doesn't point into the slope. The weight points downwards, okay, towards the centre of the Earth. Okay, the normal reaction, however, does stay at 90 degrees to the slope, so it rotates with the slope basically, and the motive force is obviously still pushing the car forwards. Now what's happened is that two of the forces are doing work. The normal reaction still isn't doing any work because it's at right angles to the direction of motion, as it was before. But now we have the motive force doing work and the weight. Now the weight's not pointing massively in the direction of motion, but it is pointing a little bit down the slope now. And if we made that slope steeper, then it would point more and more down the slope. And in fact, if we made the slope completely vertical, then it would be doing exactly the same thing as it was doing in the falling ball, because the ball's moving straight up and down. Okay? So, just because the weight is pointing partly down the slope and isn't completely at right angles, it does do a little bit of work. Not necessarily very much on a shallow slope, but it's doing something. So how does that affect the motion? Well, we've still got the motive force doing work, but the weight is now transferring some of the kinetic energy of the car into gravitational potential energy. That makes sense because the car is getting further from the centre of the Earth. It's moving upwards, so we must be gaining gravitational potential energy, and the weight is the force that is doing that job. If we're losing some of our kinetic energy that we've gained to gravitational potential energy, that means we won't accelerate as fast. We're not going to pick up speed as quickly. Okay, so that explains in terms of energy why a car cannot accelerate up a hill as much as it can accelerate on the flat. Okay, so that's a few examples of sort of qualitative descriptions of energy transfer. In the next video, we'll talk about how to do the calculations associated with that.